Hello, it's Keith here, and this is lesson 10 of the Photon series of my 65002 assembly programming tutorials. Photon is of course my Tron clone, and this is where I try and get the different systems to work as a bitmap screen for pixel plotting, even like when they're not like the NES, an actual bitmap screen, and it's a tile sprite based screen. So what we've done is we've made the tile sprite work like a bitmap screen, and that has allowed us to play our little game. Now the NES version meant some quite considerable challenges here, because to make a bitmap screen we basically need to set every tile of the visible screen to be a different tile, and then change the pixels that make up the patterns of those tiles. Now the NES screen only has a tile map of up to 256 tiles, which isn't a very tall big screen at all. So there was a trick. The pattern map can be mapped to one of two different addresses. So what I'm doing is I'm using a VBlank interrupt to set the first one, and then a line interrupt to change to the second one halfway down the screen, and that's allowed us to double it up to 512. Even that isn't enough, which is why the screen's a little bit small here, but at least it's something. Now the rather big problem though is that on the NES we can only write to these bitmap patterns during VBlank, which is very little of the actual screen time. What this effectively means is we're only able to update 11 tiles in total every refresh of the screen, which is why the clear screen effect there was quite slow. The drawing is happening quite quickly, but the display is only occurring 11 tiles per VBlank. So that's what we had to do. Now the way I've got around this is I'm cyclically updating 8 consecutive tiles, so going down the screen and then restarting over and over again every single VBlank, but then I'm updating 3 tiles, making up the 11 that I can determine. I'm actually only determining 2, the other one's unused, and those are the 2 players, the player and the CPU, and that means that they're being updated every frame, but things like the background, which really aren't changing at the moment at all, they only get updated once every few frames. Now this game has a boost mode. If I press the fire button, you can see I move faster there, and that's so I can catch up with the CPU. And the boost counter's in the bottom corner of the screen down there, and it doesn't update very well because of the updating problems. I did actually try and use the 3rd tile to make it update, and it didn't work well because of the position's not good, but the game does work fine. As well as the boost mode, the other thing I want to show you is when I press a direction and hold it, I only turn once. You have to release and press again to turn again, and that's so you don't do what I just did and crash into yourself. So I mean, it's not a perfect game because, as I say, the screen refreshes are slow, and there were things I could have done that would have been more efficient for that, but I think it's adequate for today. And as I say, really it's more about creating an example of how you can treat these tile sprite systems more like a bitmap screen. Okay, let's go over to the code and let's start discussing the challenges then. Let's start discussing them. Okay, so what I'm going to do first is I'm going to discuss the interrupt handling, and then we're going to go into the game code, and then we're going to discuss the bitmap routines. So the way the interrupts are working is we're using a cache of memory within the cartridge, because the NES has very little memory. So we've got enough memory within the cartridge to emulate the entire pattern map that makes up the 2 tile pattern sets, that the visible area of the screen. And so we're going to sort of transfer some of that during each VBlank. So we've got to first turn on the extra memory, and we do that with this command here. We write the top bit as 1 to A001. Now this is a function of some of the mapper cartridges, so you need to select the correct mapper. We're using mapper 4 here, which has that function. So that's giving us the extra memory. What we're then doing is we are defining RAM address L and H here to point to the next area within that we are copying to VRAM. So that's going to go cyclically through, transferring 8 tiles each VBlank. And then we've got the 3 that we can define that update every single time, and these are memory addresses, and that tile pattern will be transferred in entirety to the video RAM during every VBlank. Now, as I say, one possible solution that might have been better would have been to define individual pixels and update just those pixels or something like that. This was really just a generic example, you know, for you to use in your own purposes, shall we say. It's good for really any purpose. As I say, in this case it's for pixel plotting. It's adequate for the game, so I thought it would do well enough. Now we're using the interrupt handlers, and there are 2 we have to use. So the first one is the VBlank interrupt handler. Where is it? Which is just here. And then the second one is the IRQ. Now this is a function of mapper 3, memory mapper 3, and we're using it just here. And this will occur at a particular line that we define. We're defining 116. Now, the earlier systems could simulate this by basically putting a sprite and overlapping a pixel of the background or something. It seemed overly complex, and so I just cheated, if you will, and used the mapper. But I believe systems like the original Mario Brothers used to do that, so that they could have a different tile map at the start of the screen and different scroll positions. As I say, I'm using the mapper because it's easier, but there are ways of doing it without that. Anyway, let's have a look at NMI interrupt handler in entirety then. So here it is. What we're doing is we're backing up all our registers here, clearing the VBlank flag, which is something we've used in the past. This is so we can detect when VBlank occurs. We're then backing up the position that we're next going to update within the 8 sequential tiles. We're updating the 3 defined tiles here. We're using this set and send 1 tile function here to send 3, and then we are doing the 8 sequential ones just here. We're then updating the memory address so that we do the following 8 the next time. We have to reset the scroll every time we change VRAM, and then we have to set up the pages. So we're using the first set of tile patterns at the top of the screen and the second set halfway down. So we're setting the first set here, and we're also enabling the interrupt at line 116 halfway down the screen. Now, it does have to be noted that the sprite address has to be different to the pattern address, otherwise this won't work. So I guess we're setting the sprite address to 1000 here and the pattern data to 0. We've then got the IRQ handler, which does the opposite, setting the patterns to 1000 and the sprites to 0. And that disables itself because it's going to be restarted the next time the VBlank runs. The addresses of these are defined just here in the cartridge footer. Here's the IRQ handler, that's the line interrupt, and here's the VBlank, the NMI handler. The actual transfer routine to send the tiles is pretty straightforward. It's just sending data to VRAM. We select the address with memory address 2006, hit high byte first, and then we send the data to 2007, and that will be transferred to the address we specified in 2006. So all we're doing is not too difficult. Took some work getting this to happen, but basically once it works fairly well, easily, and it's not too difficult. Now, you can't really transfer much more with this. I don't think you could manage a 12th tile, but you certainly can't transfer 24 or anything. You might be able to squeeze a bit of optimization out of it. And as I say, you could redesign it so rather than transferring an entire pattern, you just transferred 1 bit plane or something like that, or even just 1 line of the bit plane. You know, I'd say there's plenty of options to make it more efficient. As I said, this was good enough for my purposes though, so I just left it at this. Okay, so that's the concept of the interrupt handlers. Let's actually look at the code. So our working screen is effectively 200 by 160. This is a tile map size of 25 times 20, and it's split in 2 parts, so it's 25 times 10 for the 2 sections. This means each one uses tiles 0 to 249 with 250 to 255 unused. We have to use some of those unused tiles to fill the blank areas of the screen, because otherwise things go a little bit weird, and I'll show you that because it's quite funny. So here we are, we're starting things up, we're just setting up our screen here, we're setting up the initial variables that are used by the interrupt handler here. This was me trying to get that accelerated boot counter to work, but it doesn't line up with the tile well at all, so it was just a mess, so I turned that off. And here we're clearing the entire screen, filling it with tile 255. Now if I change this to tile 0 and I run again, well, that title screen looks pretty good, but as soon as I start the game, well, tile 0 is now in use, so all kinds of weirdness occurs. So yeah, we don't want to use tile 0, we use 255, which is unused. And then what we're doing here is we're defining the tile maps, because apart from the border, the middle area of the screen needs to go from 0 to 249, and then from 0 to 249 twice, filling the 2 parts that we're then going to change the respective patterns to show our pixels. We're using the fill area with tiles function. This was written in the simple series. It's the same function. We're just defining a width and a height, a start position, and also a start tile number 0, and we do it twice. Now this is of course 2506 tile numbers, but that's the number's still 0 to 255. It's just a single byte in each position. It's because we're switching the pattern source within that interrupt that it's using those effective tile numbers. I guess you could call them 0 to 250 again, but it seemed more sensible to give them a different name. Okay, We're then setting up a palette here. We're initializing the destination RAM address here, and we're turning on the screen and starting the interrupt handler. And at this point, the data will be being transferred from the cache to the VRAM automatically. So now we're into the sort of general code of our game. We're resetting the game variables. They are defined within the standard NES memory at 200. We've turned on the mapper, which gives extra memory at 6,000 onwards. I think it is 6,000 to 8,000. So we're not using that for our game variables, but that's what we're resetting there, showing the main menu. And here is the start of the main gameplay. Now, because the switching from the game menu to the gameplay is a bit slow, so here's the title screen, and now I press fire, and now we've just got to wait for the interrupts to happen. So there's a delay for that to happen, and that's what this is here. This is just a delay to wait for the update to get the game screen updated. Okay, so the player can see what the background's like, and then here's the main loop. Now, as I said, in the game, you've got this boost mode, and that makes you move faster. The way it works is the game has 2 ticks. If your boost mode's enabled, you move every tick. If boost mode's disabled, you move only one of the 2 ticks. We've then got a delay here. If boost mode is on, the delay is lower, and that's so that we can update the counter in the corner. It takes a little bit of CPU power, so we need to have a different speed to keep things balanced there. We're then reading in from the controls and checking if any keys are pressed. If no keys are pressed, we're clearing the key timeout, and that's because if you press a key, you have to release it before it's registered again, and the key timeout is set, and when you release, it's released. That's what's being done there. Okay. Here's the start of the processing for the key presses. We're checking if the key timeout is set, and if it is, we're skipping over the key presses. What we do next is we clear the boost mode. We're going to set it again if the player's fire button is pressed, and then we point the 0 page entry IX to the player X acceleration, and we check the left and right directions. If the player presses left or right, we move through the directions. These are north, south, east and west, and the way we do that is we either decrement the player direction or increment it, and then we run this multi-platform function, set player direction, and what that does is it limits these to 0 to 3, the player direction, and then it reads in a new acceleration setting and transfers it to the one pointed to by IX, and that has the effect of making us move in a different direction. So that's what we do there. We then set the key timeout because we want the player to release that key before registering it again, and we continue. Now here's the fire check. We check if the fire button's pressed. If it is, we check if boost power has any boost power left, and if it doesn't, we skip over the next stage. But if we have boost power, we turn boost power on by writing a 0 to boost, and that will effectively turn the boost on. Now the rest of the logic, the handling of the boost, the decreasing the boost, showing the player, collision detection, is all handled by handle player and handle CPU. These actually do the logic of the movements, so that's all the multi-platform code, nothing special for the NES here. Now we're setting up the 2 fast refresh settings. What we're doing is we're pointing these to the tile that the player and the CPU are currently contained in, and this tells the refresh interrupt, the VBlank, to update these specially every single frame, and that means that you can see where the player goes, otherwise it would be quite a mess. So what we're doing here is we're taking the X and Y position of the player, calculating the tile map address within VRAM, and we're setting the correct memory addresses here. Here we're removing the bits that are related to the exact X pixel Y line, because we just need to have the start of the tile that the player is within. So that's what we're doing, and then we're repeating. That's the entire game loop, logic loop. Very, very small really, which is good. That's what we want. Okay, so here's our clear screen routine. When we want to clear the screen, effectively what we're actually doing is clearing patterns 0 to 255 in both the 2 pattern maps from memory VRAM address 0 to VRAM address 1FFF basically. And that's what we're doing here. So we're specifying the memory address range here, and we're just basically filling from 6,000 onwards, which is of course the buffer for the VRAM, and it will get transferred during the next VBlank. Okay, we're not going to go over the player direction reading. We've covered that before in the simple series and in YQuest. So if you need help on that, please take a look at those. What we're really going to focus on here is the PSET and the point commands, which are the plotting routines for this fake pixel screen. Okay, so first thing we're doing here is we're checking if we've been given a negative value, because to get the boost in the exact position we want with the font driver, I give it a slight negative value, but if you try and draw off screen, it creates a mess. So we are avoiding that here. And then what we're doing is we need to work out the exact position of the pixel we want to change within the byte. Now, we're working in bit planes here, and this means that a single byte contains 8 pixels, and we need to work out which position in that byte is relative to the pixel that we want to change. So basically each byte contains a pixel from 0 to 7, the bottom 3 bits of our X position, and we're getting a mask which defines that pixel's position within the data. So we're reading in one here and we're storing that in the accumulator and we're pushing it for later, and that's going to be the mask for the pixel we want to change. We're then using calcvram. What this does is it calculates the memory position within the cache for the pattern that we want to change and the line of the pattern that we want to change. So this will set HL to the correct line for the first bit plane of the pixel we want to change. We're then getting back that pixel mask we calculated before, storing it in ZB, flipping all the bits. This converts it into a background mask for the pixels we want to keep. We store that in ZC, and we're going to use those later on. Now what we do is we load in the first byte from the cache of the screen pattern that we're changing. Now this is going to be bit plane 0. We mask the pixels we want to keep, and we then shift a bit of the color we want to set. So this will be 0 to 3. If that bit is a 0, then we just store back that value we've calculated back to the screen. But if it's a 1, we all in the mask for the pixel that we want to change, and that will set that bit plane to 1 for the pixel we're changing, and we store it back again. We then add 8 to our reading position, and that's because the second bit plane is 8 bytes along from the first one in this format. And we do the same for the second bit plane here. And that will set the pixel we want to change based on an XY coordinate that was passed in 0 page entries BC here. So there we go. That's the PSET routine. The point routine is basically just the opposite. We're using calcvram again, but this time we're reading in from the screen memory, and we're basically shifting bits out into a build-up, which is effectively going to be the color that we read on from that screen position. Now, this Photon game actually only uses on or off. It doesn't care what color it is, but for completeness, we're just trying to build that back up there. Now, here's our calcvram address, which is doing the work of calculating the memory position in the cache based on an XY coordinate, and this is how we're doing it. Now the ZB 0 page entry is the X position and the ZC is the Y position. What we're going to do is we're going to load HL with the base of our cache, which is the memory address 6000 in memory, and then we're checking the Y line that we're looking at. If it's below 80, it's in the first bank, and if it's above 80, it's in the second bank. Now the second bank is at 7000, and if we're in the second bank, we're effectively subtracting 80 from the Y line, and because we're starting at 0 again, if you will, in that bank. So that's what we're doing there. And then we're going to calculate the offset within that bank for the pixel we want to change. Now the bottom 3 bits of the X position are all contained within a byte, because 0 to 7 pixels are within 1 byte, and so we need to take those out here. And what we do then is we take the remaining bits, the remaining 5 bits, and we effectively multiply them by 16. And the reason we do that is that there's 8 lines per pattern and there's 2 bytes per line of the pattern. So these bits will be a tile number across the screen, and there's 16 bytes per tile. So we're doing that, and then we're adding it in. What we do next is we take the bottom 3 bits of the Y line. These effectively come consecutively within the tile, because there's 8 consecutive lines within each tile pattern. So we're taking those and we're adding those as well. We take the remaining bits of the Y line and we're going to multiply them by 25 times 2. Why 25 times 2? Well, because they're already effectively multiplied by 8, because for the 8 lines, because we're skipping the bottom 3 bits. We need to effectively multiply by 2 because there are 2 bit planes per tile, and there's 25 tiles on a line in our virtual screen. So that's why that multiplication comes in. Now, what we're doing here is we are effectively multiplying by 2 by shifting ones to the left, and we're adding that in here, and then we're going to effectively add the value multiplied by 24 by 2 consecutive bit shifts, 1 to position 8, adding it in, and 1 to position 16 and adding it in. All this is a bit long, I know, but this effectively multiplies everything up and calculates the offset within the pattern cache within our memory of our cartridge that we want to change, and that's what we're using over and over again here to calculate the pixel memory position that we need to change to read or write our pixel. And that's what we do. It does work. It works okay. Now we've got a few other functions here: get VDP screen pods, fill area with tiles. We've actually covered all of these before in the Simple series, I think, and also in the YQuest games. So if you need to know how they work, please go and take a look at those so I don't have to explain them again, because I'm getting tired of it. So I'd rather do new and more interesting things. Anyway, that's the end of today's example. I hope you found it interesting. You can go to my website, you can download the source code, and you can download the build scripts. And I always say, if by some miracle you manage to make some use of them somehow in your own games, please go ahead. You don't need to give me credit. And if by some incredible miracle you manage to sell them and make some money, then good luck to you again. You don't need to give me credit. I really don't care. Make the best of it. That's what they're there for. Anyway, if you've liked this video, please hit the like button. If you like the videos, YouTube recommends them to more people. And it also helps me out if you subscribe, because that keeps my motivation up to make more videos in the future, because it does take quite a bit of time. Anyway, I hope you've had fun watching this video today, and maybe you'll go down and download that source code. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.